We're going to start our lesson on stoichiometry today. Stoichiometry is critically important for success this whole semester. Learning goal on the board, students will be able to convert quantities of substances in chemical reactions. That's what we're going to explore today. Identify and explain the importance of limiting reagents. We'll get to that later in the week. Calculate theoretical and percent yields. And then we're going to be carrying out a lab where we react sodium bicarbonate with hydrochloric acid. We're going to generate 3 products, and we will determine both our actual yield and percent yield to see how good of a job we've done in the lab. Percent yield's a little different from percent error, but you'll be very successful with it. Now, in order to be successful in this chapter, you need to have mastered the previous chapter on writing and balancing equations, and your test scores certainly show that you have mastered that concept. You are going to see prediction and balancing of equations in this chapter. I'm not going to go through all of that the same way I did in the previous chapter because you've already mastered it, but certainly all the new stuff we'll go through very carefully. First up, stoichiometry. The word sounds much worse than anything you're going to see in the chapter. It says the study of the amounts of substances consumed and produced in chemical reactions. If you considered a chemical reaction such as this one, for example, sodium plus copper 2 chloride yields sodium chloride and copper, which substances would get consumed? Reactants or products? Reactants. So your reactants are going to be the ones that get consumed or utilized. Their concentrations will decrease as more and more gets used. In contrast, your products get produced or generated. They get made. So that's the first thing we're going to consider. Now, stoichiometry is the study of the amounts that get consumed. So it's going to involve measuring or calculating amounts of substances. What's going to happen here ultimately is you'll be given initially the quantity of one substance, probably a reactant, and you'll be asked to determine the quantity of another substance, probably a product, but it can be reactant to reactant, product to product, etc. So if you're given, for example, 3 grams of sodium, using stoichiometry, you can determine the mass of sodium chloride in grams that should be generated. And that's going to be one of our goals for the chapter. Now, we know that coefficients in balanced chemical equations indicate moles of substance. For every 2 moles of sodium, 1 mole of copper 2 chloride will react with 2 moles of sodium. So balanced chemical equations only tell you the ratio in which substances combine. They do not indicate how much substance to use. And in a lab, it will often say mass out this amount of substance. So a balanced chemical equation only shows you ratios in which substances combine and substances get generated. It doesn't specify the quantity of substance that you will use. From balanced chemical equations, we can determine mole ratios. And mole ratios are obtained from the coefficients in a balanced chemical equation. The coefficient will be equal to the number of moles of substance. For example, in the equation I've got here, I'm going to go ahead and put some different colors in so you can truly follow along. First of all, looking at that equation, you just tested out on that, classify that reaction for me. Decomp, because you have how many reactants? 1. And you generate substances, 2 or more substances, that is elements or compounds. First question up, I've got the answers here, but let's look at it. It says mole ratio of potassium chlorate to oxygen gas. I look at the coefficient, 2 to 3. So this is a 2 to 3 mole ratio, potassium chlorate to oxygen. You can simply write the mole ratio out as such, although in some instances you're going to see in a few minutes that it also can be beneficial to write it out this way, where you have 2 moles of potassium chlorate to 3 moles of oxygen gas. A mole ratio, coefficients indicate how many moles of each you have. In the second example, the mole ratio of potassium chlorate to potassium chloride, this may also be written as the mole ratio of potassium containing compounds. Potassium chlorate is 2, potassium chloride is 2 as well. That mole ratio is 2 to 2, or in some instances it may be beneficial to reduce it down. But if they ask you for the mole ratio, you can use just the coefficients. It'll be easier for you. The mole ratio of potassium chloride to oxygen, or it could say the mole ratio of products, would be 2 to 3. And again, that number is coming from the balanced chemical equation. The mole ratio is extremely useful. It is the only way to convert from one substance to another. And in this particular chapter, you are going to be given a quantity of one substance and asked for the quantity of a different substance. And the only way that you can go from one substance to another is through the mole ratio. Your quiz will open up similarly to what you see here. It says the mole ratio allows the chemist to convert from one substance to another. For example, I may say to you magnesium reacts with lead 4 sulfide. What is the mole ratio of products, elements, and compounds? Your leaping point here will always be to write a balanced chemical equation. So you have magnesium reacting with lead 4 sulfide, and again, formula writing is critical. Lead 4 sulfide You are assessed on this concept already. You are predicting products of this single replacement reaction. You've got magnesium sulfide and lead. And you are balanced. So there's nothing new there. You've already demonstrated mastery on this concept on the previous test. First question is, what is the mole ratio of products? What's your mole ratio of products? 2 to 1. You look at the products, 2 to 1. What is the mole ratio of elements in the balanced equation? element, element. Remember, an element has one capital letter, which may or may not be followed by a lowercase. Compounds have a minimum of 2 capital letters. So what is the mole ratio of compounds? 1 to 2 is correct. And just write them in the same order from left to right. And right away you're going to pick up 30 to 35 points on your quiz. That's exactly how it will open up. Questions at this point? Okay. What we really want to delve into for the whole first half of this chapter are stoichiometric calculations. This is going to allow a chemist to convert from a quantity of one substance to a quantity of another, as I illustrated in the initial setup here, where you will be given an amount of one substance and asked for an amount of a second substance. Now, if you go into any textbook, they're going to jump in right away. They're going to give you the mass of one substance and ask for the mass of another substance. That is a 3-step problem. I have found over the years that kids had too much difficulty going from nothing all the way to a 3-step problem. So I'm going to start it much simpler for you, and we're going to build it up to that 3-step problem. The simplest thing initially will be the first type of stoichiometric calculation. This is a mole-to-mole conversion. It's 1 step. You will be given moles of one substance and ask for moles of another substance. It can be reactant to reactant, it can be reactant to product, it can be product to product, it can be product to reactant, so any combination. To carry out this type of calculation, you're going to write a balanced chemical equation. You already know how to do that. Figure out what's given and what is unknown. Set up your calculation, always starting with what you're given, and the mole ratio will be your conversion factor. Allow your units to drive the problem, and you will be much more successful with these types of calculations. You will also see why I was such a dot monster on quiz 2-3, where if you didn't put the substance in, I put a little dot, and then I subtracted a point. You are going to see why very early on here you need to indicate the substance. The framework for this probably will not make sense until we do a few examples, so I will come back to this framework in just a few minutes. The first example is done out for you. I'll walk through, and then I will do one very slowly so you can see the whole setup. It says how many moles of potassium chlorate are decomposed to generate 9 moles of oxygen gas. Here's my balanced equation. We had that previously. We want to know moles of potassium chlorate. We're given 9 moles of oxygen gas. Your given will always be a number, a unit, and a substance. Later on in the chapter, you will be provided with 2 givens, and you'll have to determine which one to use. Right now, you have 1 given highlighted in green, shown here. And what we're looking for, moles of potassium chlorate in yellow. Your given is always at the beginning. What you want to know is always at the end. Let your units drive your problem here. The units and substance in the given is moles of oxygen. I need moles of oxygen here. This number comes from the balanced chemical equation. 3 moles of oxygen gas. Mole ratio allows you to convert from one substance to another. The substance you want is on top. Regardless of what is here, it will be moles of. and this number came from the coefficient in the balanced equation. This is known as a mole ratio. The mole ratio allows you to convert from one substance to another. The mole ratio is the only time you have two different substances in the same fraction, and these numbers don't have to be 1 because they come from the balanced equation. We learned about mole to mass conversions and mass to mole conversions previously. We're going to tag those on in a few minutes. Here's the new piece right here, mole ratio. Carry out the math and you've got 6 moles of potassium chlorate. Let me walk you through an example with nothing to show you how you go from given to unknown. In the first example, it says sodium phosphate reacts with magnesium sulfide. We want to know the mole ratio of products as well as phosphate-containing compounds. Your first step is always to write a balanced chemical equation. We've got sodium phosphate reacting with magnesium sulfide. Classify that reaction. Double replacement is correct. Sodium sulfide and magnesium phosphide. Is that what you got? Alrighty. It says, what is the mole ratio of products? What would you write? 3 to 1 is correct. You look at your two products, you look at their coefficients. What's the mole ratio of phosphate containing compounds? 2 to 1 is correct. You look at the two compounds that contain phosphide ion coefficients. All right? You've got 35 points worth. The only other thing I might ask you is to classify double replacement. Here comes the new piece of the puzzle. It says how many moles of magnesium sulfide, that's what we're looking for. It's going to the right. How many moles of magnesium sulfide should react with 4 moles of sodium phosphate? That's my given. It goes to the left. Here's my given. This is what I'm looking for. Questions on the setup. If you're ever given moles and you're going to a different substance, your first step will always, always, always be the mole ratio from the balanced equation. So this is going to be my mole ratio. I do moles of sodium phosphite here in order to get the unit and the substance to cancel. This number comes from the coefficient in the balanced chemical equation. I want to get to magnesium sulfide. I've got 3 moles of magnesium sulfide. Where did the 3 come from? Balanced equation. This is a mole ratio. And then you've got 6 moles of mag sulfide. And I just want to point something out to you. I want you to truly see it here. You'll understand the dot monster philosophy. The mole ratio is the only time, Halen, that you have 2 different substances in the same fraction and numbers other than 1 before moles, because these numbers are your stoichiometric coefficients. Whatever you start with goes here. Whatever substance you want to get to will go here. If you're given moles, the mole ratio will always be your first step. You want to try the next one, or you want to do it together? Try? Alrighty. C says if 2 moles of sodium phosphite react with an excess of magnesium sulfide, how many moles of the phosphate-containing compound should be generated? I'll have you do it yourself. I want you to first tell me the given and the unknown. What's the given? 2 moles of sodium phosphite. Reacting with an excess of mag sulfide is interesting, but it doesn't configure in our calculation. We want to know moles of phosphate-containing compound that should be generated. Give it a shot. How'd we do? How'd we do? Yes, yes? Yes, yes?
I guess that's what we were looking for.
It said moles of the phosphate-containing compound that should be generated. What gets generated, reactants or products? Products. So the products get generated. So you know we have to look at the product side. And which product contains phosphite? That one. And that's why we were going after that one. Alrighty? Mole to mole conversion. You're given moles of one substance. You want moles of a different substance. When we work in the lab, we work with masses of substances. So ultimately, we're building up to a mass-to-mass conversion. We'll do it slowly. If I give you moles of one substance, and I want to know the mass of this substance. I know how to get to moles. How do I convert moles to mass of the same substance? I use the periodic table. So in the next type of problem, you're going to be given moles and asked for mass, and instead of stopping here, we would do one additional step. And that's what you're going to see right here. We're going to look first at a mole to mass, and then we'll do it backward with a mass to mole conversion. Also, before moving on, let me backtrack to your framework right here. If you are given moles of one substance and you're converting to another substance, your first step right here is always the mole ratio. Note that the moles of Q will cancel, and you'll be left with moles of R, which is what is desired. Here, you'll see the same beginning point right here. If you're given moles of Q, you will first use the mole ratio to go from Q to R, and then this step right here, you already know how to do back from chapter 7. It's just a matter of integrating it in. This is right off the periodic table. Again, you will note that the mole ratio is the only place you have different substances. And when you're converting from moles to mass of the same substance, you always have 1 mole of it because you're going off the periodic table. So you're going to do the same thing we did previously with one additional step. And most of you are already going ahead because you're like, I can do this, so I better catch up. It says sodium reacts with iron to carbonate. Sodium reacts with iron 2 carbonate. Single replacement reaction. We've got sodium carbonate and iron. So we've written the balanced equation. B says what mass of sodium should react with 2 moles of iron 2 carbonate? What's the given? 2 moles of iron 2 carbonate. That's what I'm going to start with. And what do I want to get to? Mass of sodium. If you are ever given moles and you want to get to another substance, your first step will always be the mole ratio from the balanced equation. That's the new piece you learned today. You've got 1 mole of iron 2 carbonate, 2 moles of sodium. Let your units drive you. Cancel, cancel. Now, if we had a mole ratio problem, we'd be done. But we're asking for mass. Here, we're going to convert from moles to mass, same substance. It is the mole ratio that allowed us to go from one substance to another. This piece you know how to do. 1 mole of anything, in this case sodium, is equal to the mass in grams. And again, look at that cross cancellation of units. Mole to mass conversion. This piece you know how to do. Let me point out a few things. I know I sound like a broken record, but I think it will help. The mole ratio is the only place you have two different substances, and you can have numbers other than one because they come from the balanced equation. When you go from mole to mass, you have the same substance. You always have 1 mole of it.
For the, never mind.
All right, look at C. It says if 3 moles of sodium react with an excess of iron 2 carbonate, what is the mass of the element that should be generated? What's your given? 3 moles of sodium. What do you want to know? The mass of the element generated. What element gets generated? Iron. If it's generated, it's a product. The only element on the product side is iron. There's your setup. See if you can rip it. Don't look up till you're done. And when you're done, look up and see if your answer matches mine. How we doing? Piece of cake, huh? We've got mole to mole conversions. We have mole to mass. One more piece of the puzzle for today. I want to do it backward now. If you're given the mass of one substance, I want you to calculate the moles of the other substance. Framework will be slightly different. You're just running it in reverse. So in a mass to mole conversion, you want to convert the mass of one substance to moles of another. You're going to run it backward. If you're given the mass, the first thing you're going to do is convert it to moles using the periodic table. Then you will use the mole ratio to go from one substance, that is Q, to the other substance, R. Let's take a look at a few examples together, and then you will be practicing. The example says lithium sulfite reacts with iron 3 oxalate. Single or double replacement? Double. So that's the only information given, but you are very solid with your prediction. So you get lithium oxalate and iron 3 sulfide. What would be the mole ratio of reactants? 3 to 1. Good. I just want to keep asking those questions. You'll see it on the quiz. So that's step A. We've got a balanced equation. B says how many moles of iron 3 oxalate should react with 123 grams of lithium sulfite? What's my given? 123 grams of lithium sulfite. And what do I want to know? I want moles of iron 3 oxalate. That got a little squishy. The first thing I need to do is a mass to mole conversion, same substance. This you learned back in chapter 7. It's just a matter of linking concepts together. 1 mole of anything is equal to its mass in grams. And now we want to go from moles of lithium sulfite to moles of iron 3 oxalate. And this is going to be a mole ratio. Where does the mole ratio come from? Balanced equation. So you've got 3 moles of lithium sulfite, 1 mole of iron 3 oxalate. And again, let your units drive your problem. If you have more than 1 quantity in the denominator, bracket them off so that you don't make a calculation error. In the calculator, 123 divided by open parenthesis 93.945 times 3, close parenthesis, equals, and you have 0.436 moles of iron 3 oxalate. So again, you start with the mass. You convert it to moles. This is coming off the periodic table. Anything off the periodic table is grams per mole. So you'll have 1 mole. Your mole ratio comes from the balanced equation. The coefficients are what you're inserting here. You will have 2 different substances in the mole ratio. And now you should start to see why it's so critical to label your substances to drive your problem. Let's try and set up C, and you'll give it a shot. It says how many moles of each product. So this is a little trickier. They're asking for 2 pieces. They want to know in C moles of both products. When you're given 148 grams of iron 3 oxalate reacting with an excess of lithium sulfite, what you're given? 148 grams of iron 3 oxalate Which one do you want to get to first?
The second one.
That it doesn't actually matter. You want to do this one first?
Yeah.
Okay. How are we going to get there? What's the first thing we need to do? Convert mass to moles of the same substance. 1 mole of anything is equal to the mass in grams off the periodic table. Once we're at moles of one substance and we want to get to moles of the other substance, what do? Mole ratio from the balanced equation. We have 1 mole. This is what we want to get rid of. This is what we want to get to. And that's going to be 0.394 moles of that product. How do we get to moles of the other product? We have 0.394 moles of this product. How can we get to moles of the other product? How do you go from moles of one substance to moles of another? Mole ratio. What are you going to put in? What goes here? 1 mole. Where'd you get 1 from? Is it always 1? No, you got it from the coefficient. And you need the substance you want. How many moles of this do you have? Where'd you get 3 from? Coefficient in the balanced equation. And you have 1.18 moles of the other product. Now, I didn't give you anything so nitpicky where I asked you to do that, but I thought it would be a good wrap-up because you can see mole-to-mole conversion. And again, let your units drive your problem. You can see mass-to-mole conversion, and up at the top we did mole-to-mass. This will all build to mass. Stoichiometric calculations are very, very important in chemistry. You should have a feel for what stoichiometry is and be able to do simple calculations. I'm going to give you your classwork, and I'm going to ask you to do the following problems on your classwork. You can do number 1, 2A through D. And you can do F and G in terms of what we did. That will really solidify your understanding of stoichiometric conversions, and you'll see where we're going with it next time.